Okay, so we've learned in the past lecture some basics about the formalism of thermal field theory. And so today in the last lecture I wanted then to outline some kind of an application. And so of course then the style will be a little bit less detailed because this is, let's say it's kind of in some sense a research topic that it was only worked out like less than 10 years ago or so, this computation. So we won't go through every little detail, but still somehow it's an example of how quite a few of the things that we discussed, they somehow play a role. And so in particular what I want to show is something which is quite interesting usually in sort of analytical computation, which is if you find a logarithm. And so then we talk about leading logarithm, leading log. So logs are special because the log has an argument, and the argument is usually the log is especially if there is a ratio of scales in the argument. And the ratio of scales is nice because then this means that you can understand it either from the side of the small scale or you can understand it from the side of the large scale. And so these logs are kind of more universal than other fine details of the result. And so that's another reason why it's sort of interesting. In particular, this leading log, we can derive it with this hard thermal loop effective theory that we introduced yesterday. So now, before we get there, just some motivation. So there are thermal backgrounds of many things. And photons, that gives us the CMB that we have seen about also today in the morning. Then there's a thermal background of neutrinos. And this has not been measured directly, but indirectly we know about that. For instance, yesterday in the student talks we heard about this parameter N effective, and the N effective is an indirect measurement of the thermal neutrino background. And so now the question really is then, could there also be a thermal background in gravitational waves or gravitons if I use the same particle language? And this, well, for sure has not been seen yet, but it's also, if it's there, it plays a role. For instance, if it would be large enough, we can say that, like yesterday in the talk, we saw that if one has something else than the neutrinos, they also contribute to the N effective. If you have some additional species, they give a contribution to the NF. We call this like delta NF. And if we are able to measure precisely enough N effective, then from the result we can also deduce if there's something apart from the neutrinos in the early universe at that time. And so that's one reason, just to say that in principle, if there are gravitational waves, gravitons, a thermal background of them, they could be measurable. Now there is a difference, however, in these two and in this one. And the difference is that for photons and neutrinos, the way that this thermal background is born is that we believe that these were for a long time in equilibrium. And then at some moment they decoupled. There was a last scattering for photons, and there was a decoupling for neutrinos. And that's what we see, the thermal background, which used to be there, but then decoupled. For gravitons, to the best of our understanding, it's very unlikely that they would have ever been in thermal equilibrium. But still, they are produced from thermal scatterings, and that's what I want to illustrate today. And and therefore there is a background of them. Okay, so now before we get there, sort of a overview of gravitational waves, spectrum of primordial gravitational waves. It's called MGWs. And so I think these kind of plots, you will be shown a lot of them in the later lecture on gravitational waves, but what one can plot, for instance, is this omega, the energy fraction that we saw this morning, but now in gravitational waves. And so there is not so much in there, and so these are numbers then that typically are small numbers. And then often we plot this as a function of the current frequency of the gravitational waves. And there's a huge range of frequencies that we may consider. So let's say from 10 to 12. But in fact, extending also to the left. So there's a huge range of frequencies of gravitational waves that we are discussing. And so now that the plots that then one always sees is there are some physical mechanisms which produce gravitational waves, but in most cases very little. So we are somewhere here down. And then there are experiments, and then they try to see gravitational waves, and of course they would be good at seeing them if they had lots of energy density, if there were many gravitational waves. So there is, for instance, a plot, some curve here, which will be the future LISA sensitivity, and then there are many other future experiments here and there. And then there is also some curve that one puts somewhere here that would be like the current knowledge about how large the delta in effective can be at most, or maybe some future improvement on that. And so these are sort of the upper bounds, or what we would hope to find, the signal that we would hope to find so that we could actually observe them. Okay, somewhere here, a bit to the left, is also the pulsar timing arrays, which very much in the press recently, 10 to minus 8 or so. Yeah. Okay, and so now the thermal background that I will be discussing, it is actually very much the same, has a similar shape as the cosmic microwave background. So it is some kind of, it's like a Planck spectrum, more or less. It's not exactly a Planck spectrum, but more or less. And in fact, it is peaked at very high frequencies, sort of microwave frequencies, like the CMB. And microwave frequencies in terms of hertz, they are like 10 to 11 or so hertz. So there is some kind of a spectrum here. And what we then don't know actually for the gravitons is the amplitude of this spectrum. And the amplitude depends very much on the physics in a very, very early universe. Because the nice thing about the fact that the gravitons don't thermalize is that they don't lose memory of their past. Once they are produced somewhere, even in a very, very early universe, they just come directly to us. And so we can see to very early times with gravitons in principle. Very early times we think it's a very, very high temperature, lots of energy in every scattering, and then you could produce many of them. And so indeed it then somehow turns out that how many you produce depends very much on the maximal temperature of the early universe after inflation. And so let's say if for some reason the maximal temperature would be of the order of the Planck mass, then you might produce sort of something interesting. If it's much less than the Planck mass, then you produce less. And so then it's we don't know what the maximal temperature is, but there was some maximal temperature. We have certainly some background, and how far it's from the detection then depends on how the detection evolves and what the maximal temperature was. So that's why this is in principle a well-defined sort of interesting computation that we would like to know, well, what is the amplitude here given some maximal temperature? Okay, then there are many other processes, and of course, well, like many of you are working on phase transitions, there one is hoping then to have some extra signals from this or that, and then one might get closer to the observation. Okay, so that's what we would like to do. So now I want to show why do we produce these gravitons even if they then don't thermalize. And so how can we do that? Well, we can do that now by using these Boltzmann equations that we discussed. So Boltzmann equation would say that there's some phase space density of the gravitational waves, and it evolves with time, and it is then 2 times energy. I denote now they are on shell, and K is the again the absolute magnitude of the momentum of the gravitational waves. And then there is a phase space integral as we've had them, and then some matrix element squared, and then these ends or phase space distributions of something in the initial state, something in the final state, minus the inverse processing principle. Yeah. We write this more precisely later on. And so this is what we would like to now do. And so to go in that direction, we first have to think about the matrix element. What kind of processes are there? So now, what processes are important? So, okay, so these processes, they involve scatterings of particles. And so very often in cosmology, when we think about some physics, then somehow the tendency is to take like scalar fields because they are simple. But now we want to be a little bit more realistic, and actually what I will kind of have in mind is mainly, let's say, gluons. Let's take gluons as an example. Why do I take gluons? Because gluons, that's the species from the standard model which has the largest number of degrees of freedom. So there are many gluons, and they are also interacting more strongly than most other particles. And so if they are strongly interacting, then the matrix elements will be larger, and so it's likely that the gluons actually produce more gravitons than some more weakly interacting particles. Okay, so now, how do gluons couple to gravitons? Well, we know Einstein equation says that the Einstein tensor is 8 pi over Planck's mass squared. This is what was the gravitational, well, the Newton constant in the previous talk, and then times the energy momentum tensor. So gravity couples to the energy momentum tensor. And now any particle carries energy momentum. So therefore, any particle species, if it has energy momentum, it soars these gravitational waves. So we need the energy momentum tensor. Now, energy momentum tensor of Young-Mills theory. In Young-Mills theory, we have F, the field strength tensor, and out of that one can build an energy momentum tensor. And a part of it is just that I take these indices here and then I contract the other indices. That is part of the energy momentum tensor. There's also another part which is where I put the indices together, but it turns out that that's not important for gravitational waves because it's something proportional to g mu nu. We say it's a trace part, but gravitational waves, they have to be transverse and traceless. So somehow this is too symmetric to produce gravitational waves. This has enough structure to produce gravitational waves. Okay, so now we remember that F mu nu, it has, in terms of field, elementary fields, it has like, it can have a single field, or in a non-abelian theory, it can then have also two fields. And this then couples to gravitons. So now single field, single A, single gluon, I'll denote by a curly line, and a graviton I'll denote by like a double line, because it's sort of, if this is spin 1, then this is kind of spin 2 particle. And so now the question is what kind of vertices we get from there. And so vertices now, the simplest vertex I can imagine is that I take a single gauge field from each of the F, so I have two gauge fields, and then this couples to a graviton, to gravitational waves. So that would be a vertex like gluon, gluon, and it emits, they come together and combine to give a graviton. This vertex is somehow, it has to be inversely proportional to the Planck mass, and to work out what it precisely is, one has to watch out a little bit. I mean, here you would think that it's proportional to 1 over Planck mass squared, but that's not quite the case, because we have to, when we write then the G, we write there some metric perturbation, and one has to rescale the metric perturbation such that they appear in a canonically normalized way, like normal fields. Otherwise, we cannot do normal Feynman rules. We have to normalize them correctly. And so if one does that normalization in the right way, then it turns out that actually what appears in this vertex always is like the square root of that, of the Newton's constant. So I'll just write 1 over Planck mass here in the vertex. Okay, so it looks like there's this vertex. However, we should notice that this process is not allowed kinematically, because if we have 2 to 1 or 1 to 2, then always the mass of one of them has to be larger than the mass of the other two. Otherwise, it cannot, if this guy was heavier than the other two, it could decay into the other two. But if all have the same mass, it's not allowed. One cannot, with the same mass, you cannot decay into two other particles with the same mass. And these are all mass. Gluons are massless, graviton is massless. So it is just not allowed. It's kinematically forbidden. But this is only for this particular process. Then we can construct other processes. For instance, we can take two gluons out of one of these Fs. And I could do this kind of a diagram. When I now take two gluons here. And since there is one more gluon, then I get one more coupling, G. And so this vertex is proportional to G over Planck mass. And this would be allowed. That's completely okay. These are all massless particles, but when if you have 2 to 2, there's no, you can put any energy inside, and the same energy goes out in kinetic energy. There's no kinematic constraint for 2 to 2 scattering. That's okay. Also, another thing we can do is, general relativity is not a renormalizable theory, as we know. And so if we express it in small perturbations of the gravitational field, it means that there's not only this one single graviton coming out, one can put any number of gravitons coming out. And so in fact, one can also put a vertex where I keep 2 gluons in the initial state, but instead I put 2 gravitons in the final state. That's also allowed. Again, a 2 to 2. The problem is that whenever I add gravitons, I get one over Planck mass squared. So this is 1 over more Planck masses. So this is proportional to 1 over Planck mass squared. And so, of course, in our units, if we are at energy scales less than the Planck mass, then the Planck mass is a large number. And so if there's more suppression, then it's likely that this process is much less important than this process. Here there is also a coupling, but the gluon coupling is of order 1. It's just a number, and so having less suppression is good. But in principle, there are these processes, and of course there are infinitely many other processes. Then you can also take 3 gravitons. May look like it's better to produce more gravitons, but it's not, because it costs more. And so this now already indicates that the best thing is to produce out of a single vertex as few gravitons as possible, because it's least suppressed. Okay, so now, however, there's also another thing that one can do, because we have this vertex for producing gravitons, but then also the gluons, they interact with each other. There is a cubic vertex proportional to G. There's a quartic vertex proportional to G squared. And so we identified this as a good process, but we can do another process which actually is of the same order. Namely, we can take this diagram, but then we say that one of the gluons is not on shell, but instead it's a virtual gluon. And then we put here another vertex. And so now this vertex is 1 over Planck mass, and this vertex is G. And so in total, it's the same vertex as this one. So why would I bother doing what looks like a more complicated process? The reason is that actually this kind of process, sorry, it's a bit, this kind of process, when one has some kind of a virtual gluon here, then when one does a few computations with Boltzmann equations, one may soon realize that these look kind of, let's say, dangerous or interesting, depending on what you want to do with that. Because what you can do is, let's say we want to produce this graviton, and I'll denote its form momentum by K. I can take some energy here, and I can put most of the energy to the graviton. And here I can take some other energy. I can put most of that energy here. And so energy is flowing here, and this process is taking place. And if I manage to arrange kinematics such that there's very little energy on this rung here, as we call it, then the propagator, there's still a propagator. Propagator is 1 over the momentum here squared. And so if there's very little energy here, then this propagator can be large, and it can enhance this process. And so this kind of T-channel scatterings are often very important because they can be enhanced by the exchange of some soft gauge fields. Well, in fact, the fact that such diagrams can be important should be familiar, because if you think about, if we would like to do like hydrogen atom in terms of Feynman diagrams, then it's precisely the same type of diagrams which play a role. We have some E minus and P plus, and then we exchange many photons, and it's the exchange of many photons that binds these two together. And these are, again, so to say, soft photons exchange, but there can be many of them and they can have a big effect. And in some sense it's a bit like this, although it's also different because this is non-relativistic and this is relativistic. But still, the fact that these T-channel exchanges can be important is quite common. Okay, time is running in this direction, maybe here. So now we would like to look at this, and it turns out that this is really what gives us this leading logarithm. And so I'll draw the diagram maybe a bit. I draw it again, maybe a little bit bigger. And so this is K. And then I denote this momentum that we are exchanging here. This I call P. And here is a vertex, and this is a vertex from this energy momentum tensor. So it's like a gravitational vertex. Here is some for momentum Q, which is K minus P. And then here is the vertex, but this vertex is not from the energy momentum tensor. This is a usual gauge vertex. And then there are some momenta here, R and R minus P. Okay, so now we have drawn a diagram. We could take the Feynman rule for this vertex, for this vertex, for this propagator, put everything together and compute the m squared. And of course, if we want to do a precise computation, that's exactly what we would do. But now, now we have learned all these things, and what I want to now do is I will want to do a more clever thing, which is sufficient for finding this logarithm. Because doing the full thing, it's quite messy, because this vertex is, okay, 3-gluon vertex is already complicated, so to say. And if you instead have a energy momentum tensor, it's much more complicated already. It's quite complicated. So it's not something that one can do on a blackboard. However, what we do now is let's say we assume I'm interested in producing gravitons with momenta, and these momenta I will take to be what we yesterday called hard momenta. So some momenta of order temperature, and I always like to put this pi there, as we discussed yesterday. So these are kind of typical thermal momenta. And so I'm asking how many gravitons would I produce of those. And then we consider, indeed, the case that this transferred momentum P here is soft. Because that seems to be the most interesting or potentially dangerous or potentially important contribution. So P0 and momentum are soft, are maybe of the order of g times t. And so if we ask what is the contribution from this domain, it's not the full answer, but it's part of the answer, then we know from yesterday, we could anticipate from yesterday that, okay, now my gluon here is is soft. These guys can be hard, but this is soft. And if I focus on what this guy is doing when it forms the graviton, then I can treat all of these things here as if I had already taken them into account when I consider the properties of the soft gluon. And what I'm saying, what this means is that I treat this, all of this is included in the HTL self-energy of this soft photon. And more precisely, this is a real scattering. And real scattering is like a rate, something is happening. And something is happening, a rate is an imaginary part. And in fact, this part is really corresponds to what this Landau damping part I mentioned. But we don't need to, fortunately, we don't need to track down the precise spot where it is Landau damping or not, but that will turn out to be the case. So that's now the picture that we have. And so then it's, why would I do it like this? Well, the way I do it like this is that then kind of the problem simplifies. So on one hand, it's maybe sounds more complicated because I'm using some effective theory rather than 9 Boltzmann, but it simplifies because then it's again like a 2-to-1 process. And so the kinematics is much simpler than 2-to-2. So now we have the ingredients, and now we want to put everything together. And so the first thing is, kinematics. Of this 2-to-1. So Q plus P going into K. So this is the graviton, and this is on shell. It's an external particle on shell with hard momentum. This is a gluon. This gluon is also on shell, massless gluon. But the one thing we learned about the HTL yesterday is that HTL, this resummation, what it does is that then the resummed gluons, they are not necessarily on shell. They can also be off shell. They have like a spectral weight. So this we cannot assume to be on shell. This is some form momentum which can be off shell. And so this means that when we do then the phase space, then normally if we were writing the phase space for 2 particles coming together, we would have d3p 2 pi cubed times 2 times the energy. If it were on shell, d3q 2 pi cubed 2 times the energy, and then the energy momentum conservation. But now we cannot use this because this would be on shell. So instead we replace this by this 1/2 EP. It kind of comes from the on shell, and so instead we replace it by integration over momentum over the energy. And so we haven't, these are independent, we are not on shell, these are independent variables. And we have this kind of a phase space. So integration over P0, integration over P, integration over the momenta of that on-shell gluon, then energy momentum conservation. And so now, but still it's 2-to-1. So even if we are not on shell, it's not too difficult. And so that's then one of the exercises And indeed one can rewrite this, and what the exercise says is that one can, I can integrate, we can integrate over Q by using the spatial part of this energy momentum conservation. Then there is still P0 and P, and one can also integrate out over some angles of the P, and then there is still a two-dimensional integration left over. And at the end of the day, we can write the two-dimensional integration. We can keep the P0 as an integration variable. And then we have another integration. And actually, it turns out to be helpful to write this other integration as integration. One could write it in terms of an integration of the absolute value of the P. But in the exercise, I instead write it as a function of what we call P perp squared, 16 pi squared K, where the P perp squared is P squared minus P0 squared. And this is positive or non-negative. And this means that the spatial momentum is larger than the time-like momentum, so we are space-like. This is space-like. So this kind of T-channel scattering, if the particles are massless, then the T-channel scattering is always space-like. In sort of classic particle physics, we also call this like deep inelastic scattering or so, and that's also very much space-like. So it's in space-like scattering. Okay, so this is now the phase space. So that we will need. And so this is one part of the computation which one can really work out fully without knowing anything about the HDL and so on. Okay, so that's one ingredient. Now, what else do we need? Then we need the phase space distributions. And the phase space distributions, this we also can extract from the Boltzmann equation, because from the Boltzmann, what we now have learned is that if I have this type of a process, then there are always two possibilities. There's first the possibility that these are in the initial state, this is in the final state, and these are now bosons, gluons are bosons, these are bosons, so then I would get Bose distribution of the gluon. I assume the gluon to be in equilibrium, so it's really the Bose distribution. I have this gluon here, also in equilibrium, and then the graviton would be in the final state. So then I would have 1 plus, and the graviton I don't know if it's in equilibrium. Most likely it's not, so I'll just put in some F of the graviton. And then I would have the inverse process. In the Boltzmann there's always the inverse process. So now instead the graviton in the initial state, and then these guys in the final state. But now, what we do is we already anticipate what I said. Actually, the proof of this statement is then we can see it afterwards, but we are kind of now anticipating it. That actually the gravitons, if we produce them, we will not produce enough of them to be anywhere near equilibrium. So actually this graviton phase space distribution will be very, very small. So I will drop this term, drop this term. And so then I'm only producing. I'm not there's no loss term, there's only a gain term. And furthermore, here I can write this Q0, this is then my K minus P0. Q is k minus p. I think I had it here already, k minus p. So therefore this is nb k minus p0, nb p0. And now we come to the assumption that this, I'm producing hard gravitons, so k is large, but I'm looking at the contribution from small p0, soft gauge fields, soft gluons. So then p0 is much less than k, and so here I can put p0 to 0, and here I cannot put it to 0. Instead, this is the Bose enhancement that we also discussed at length. So that's another reason why in the thermal context this kind of soft gluons are very, very important, because they are, again, Bose enhanced. So we saw that we saw yesterday that the Bose distribution at small energies, it goes like temperature over P0. There are many of those. They can play a big role. Okay, so now we know the kinematics, we know what happens with the phase space distribution. Then there is the difficult part, and that's what happens with the vertices, determining the matrix element squared. And so here I will be kind of quite vague, but we have to say something. Well, the important thing is that we only have to discuss this vertex. What happens with the other vertex is part of the HTL, so we only need that. Okay, so now so what we do remember is that this comes from from the energy momentum tensor. And now we are taking two, from each of these we are taking one gluon, but this has two indices, so then there is the derivative which acts on that. And derivative in momentum space gives a momentum. So this is therefore quadratic in momenta. Okay, that's one thing to remember. And now, okay, we need this diagram all the time, so I'll draw it again here, but now I just put my P, K minus P, and K here. Okay, so we have this K and we have P. We have only two momenta, so it's quadratic, so it can have something like KK, it could have KP, it could have PP. These are the quadratics that I can build out of two momenta, and then the indices would have to be somehow sorted out. Now, we want to produce a physical graviton here, and physical graviton is transverse. It's traceless transverse. Spin 2 particle transverse, like a physical photon is transverse. So for propagating graviton, we need transverse projection. And so transverse with respect to k vector. That's the direction of propagation of my graviton, and we need something transverse with respect to that. So this means I cannot take the part with two k's, because if I have k's, then there's only the k vector. Out of the k vector, I cannot make something which is transverse with respect to the k vector. On the other hand, I would like to have k. Why would I like to have k? Because k is the hard momentum. Hard means large, and I want to estimate what is the largest contribution to this matrix element. So actually this kind of a mixed term is a good term. And however, we have to in order to get this transverse part, then the only way I can get the transverse part is that I get the transverse part from the p, because the k is just gives me the direction, and if I want something transverse, I have to take it from the other momentum. Okay, so now I know this is quite vague, but that's effectively what I want. I want the k. From the k, I want to keep the k, and from the p, I then want one transverse part. Okay, so now then there's one more thing that we need to do. Okay, this we will need in a moment, but I'll take it away now. So we have kind of, what we have done is, we have sort of postponed the discussion about what happens with this soft gluon all the time. We just said that we are HDL, treating it with HDL, but we didn't really say what we do. But okay, yesterday we learned something about the HDL. We learned that there are these two different polarizations. We had the transverse polarization and then we had the what we call the electric polarization. And then there were the corresponding spectral functions, rho t, rho e. So now what we see is that, this particular structure, this transverse structure, it couples to both the T and the E. It couples directly to the T by definition, but it also couples to this E because I have subtracted it here. So now it is this transverse part which is interesting, because suppose you take this K, this large K here, and let's take in the end we need matrix elements squared. So somehow from each M we get one K, and then we can contract these Ks with the PT. And so let's see what happens. And so I apologize because I realized I'm using again these Euclidean conventions as well as I was doing yesterday, but most of the time I was Minkowskian. But it really doesn't matter for the spatial part because it's anyway spatial. So in fact we can just put the indices up and see what happens if we project that with this guy. We get, so only the spatial indices play a role, then there would be a minus sign, but because there are two spatial indices, the minus signs cancel, so it doesn't really matter. So I get K squared, the spatial part squared, then minus K dot P squared over P squared. So K squared, P squared minus K dot P squared over p squared. So what is this? So what you see here is the momentum projected in the direction of the k. But then here is the full momentum, and then we subtract the projection in the direction of k. So what's left over is the transverse part. So in fact, this is precisely, I'm now defining, I already defined transverseless with respect to k, and so in this subtraction, left over is precisely the transverse part of the momentum. And now we see it's nice because also from the k, only the spatial part survives, and the spatial part is hard. It's the hard momentum. The virtuality of the graviton is small, so if we would have gotten the 4 momentum squared, it would be bad, it would be 0. But now we get out of this, we get the transverse part with the spatial part squared, and that's large. So we get this kind of a combination. Okay, so now we can put everything together. Now we put everything together, and so let's see what comes out. So we put everything together like in a Boltzmann equation. 1 over 2k. Okay, then in this vertex there was this 1 over Planck mass. So when I take the square, then it's like 8 pi over Planck mass squared, let's say. Then we had the phase space. There was dp0. There was d3 p perp squared over 16 pi squared k. Then there were the phase space distributions, nb, k, t, p0. And then there was this vertex, this projection k squared, p perp squared, p squared, and now we have to remember p squared minus p0 squared is p perp squared, so p squared is p0 squared plus p perp squared, so I can write here p perp squared plus p0 squared. And then I'm still missing one thing. Here there was one p perp here, and we took the other k, and that we discussed there, but there was this one still left over. So actually there is another p perp squared here. And then what I'm still missing is these spectral functions. There was the spectral function rho t from here, and then with minus sign the rho e. So we get this kind of an ugly looking integral, but now of course this is precisely the integral that which was in the exercise yesterday, and so it so happens that by doing this we get this nice integral for which one can establish this sum rule. Okay, actually let me cancel the k, and k, and then this is exactly what we had. So there's complicated physics taking place on this light cone, all these t-channel scatterings, but we know that that the proper effective theory is this HDL. The HDL is complicated because the self-energies are complicated, because the spectral functions are complicated. But if we are close to the light cone, there's this mapping from the HDL to something much simpler, which goes via this sum rule. And the sum rule says that this integral, 1 over p0, this difference, and this weight is very simple. It's p perp squared minus 1 over p perk squared plus the electric mass squared, the d by mass squared. And now we are pretty far. Now we can just put everything together. Sorry, I should take one of the pi's. There was a pi here. I should take one of the pi's and put it there. Then it's correct. Okay, so there's 8 pi here, 16 pi, so 1 over 2. There's 1 over 2 here, so 2 m Planck squared. Then we have the NB. Then we have the temperature, and then we still have to do then still this integral. In the exercise, there's also the upper bound of this integral is 2k squared. And then what is the integrand? The integrand is as this guy and these guys. I can put these guys together. If I put them together, I get p perp squared plus me squared. If I put it there, I get this one, and then I subtract there, I get minus p perp squared. These cancel, and then there is this p perp squared here. Cancels again this one, and indeed I get a very simple integral. I think I missed the factor. Here is 8 over 16 is 1 over 2. Here is 1 over 2, so it's 4. Times the d by mass squared times the log dx divided by x plus something is a log. So it's a logarithm of me squared plus 4k squared. That's the substitution on the upper boundary, and then the substitution on the lower boundary gives just me squared. And actually, now we have to remember that we were not doing the full computation, we were doing a partial computation, just looking at what comes from small momenta. And so we were always assuming that this k is a large quantity, so k is of order pi times t, whereas the me, the d by mass, it's a small quantity, so of order g times t. So really, to be consistent, we can omit this one. And so then we get this, okay, let me rewrite the result then. I rewrite the result. Now I rewrite the result. Maybe I even rewrite it in a more complete form. So even the left-hand side I could rewrite now as we saw that it is. It's expanding background. It's really kh dk. Of the gravitational wave phase space density. That is now has the structure that there is a gamma gravitational wave, and then there is one equilibrium distribution here, and then we discussed previously that this is the gain term. And in principle, we would expect that there's a loss term, because in equilibrium, right-hand side should be 0. But we don't see the loss term now, because we have put it already to 0. But at least we get this structure, because nicely we have here exactly the Bose distribution. It's very good that we have here the Bose distribution, because the energy of the graviton must come out from somewhere. And so this says that it comes from with a Bose distribution from the thermal fluctuations in the thermal plasma, in the gluon plasma. This is the gain term, and then if we write it like this, then we get then we can write that the gamma GW is me squared, and this t was here, an argument was k, so me squared times t divided by 4 Planck mass squared log 4k squared me squared. Okay, so this is now our result. This is the leading log that I announced. It's a leading log because it has two different scales. K is a large scale, pi times t. Me is a small scale, g times t. If I can write it as log I can write it as 2 times logarithm of 2 times k divided by then g times t. And so now you see it really has a log of the coupling. And so that's very characteristic. That's the leading log. That means that this process is logarithmically enhanced with a small coupling. And that means also, it means that the perturbation theory breaks down. If we had good perturbation theory, there cannot be, then the coupling is only in the vertices. Here we get the coupling inside a log. So that's a manifestation, that's something that the medium properties really play a role. And however, since it's a log ratio of 2 different scales, then it also means that our computation, which was a partial computation, it was really correct only for this soft momenta. But since this soft momenta appear here, then it is a correct computation for this soft momenta. What we are missing is that if we would have done really like a full computation, then there would be something next to it without the log, some numbers, some functions, maybe of the momentum or so. But the log is there, and it's important that the log is there. It's important theoretically because it's intriguing that you get a coupling, but it's important also just by showing that then the result is non-zero. Even if we didn't compute this, it cannot go away. There's no way that from the simpler processes, but more complicated to handle in practice, that you would get another log of g. It can only come from this soft domain, the log of g. So it's non-zero, it's there. Okay, I think this is sort of quite typical to what happens in then thermal field theory. If you have something, like gravitational waves, gravitons, but also many other particles, light particles, dark matter particles maybe, right-handed neutrinos or so, which happen to be light compared with the temperature. That fact that you get some logs of this type, that's very typical. And so it's then where we need tools of thermal field theory to compute this correctly. But now let me still come back to what this really means. What does it mean? What should we learn from this kind of a number? So the usual thing we do in cosmology is when we get some rate, so like here the production rate of these gravitons, is that we have to compare it with the Hubble rate, or the age of the universe, or the inverse of the age of the universe, the Hubble rate. So let's compare gamma GW with Hubble rate. So the Hubble rate, So something about this morning, but maybe not yet. But I mean, in a thermal medium, the Hubble rate is sort of proportional to t. Well, it is proportional to t squared over the Planck mass. And then there are some numbers, but now we don't need the numbers. That's the order of magnitude here. And for this, we now we have here the expression, but I can write the expression now again in terms of the couplings. So me is like g, so it's g squared, t squared times t is t cubed times then 4 times Planck mass squared, and then some log. And of course the log, it's difficult for us to give a numerical value to this log, but the log is never in cosmological order of magnitude estimate. Logs are of order unity. They can be, maybe it's 5, maybe it's 10, but usually it's 2 or minus 1. Well, it should be positive, so maybe 1/2, but it's of order unity. So what I will do now is I will plot these results, and so let's plot these results. It's a function of t, and Hubble rate, well, it's a parabola. And so this rate here is just, it's a higher power, t cubed. So it grows more slowly at small temperatures. But then at some point it starts growing faster. And so yes, I mean, at some point this gamma becomes larger than the Hubble rate. But now when does this happen? Well, when does it happen? We can just equate them, and let's forget about the log. So we equate them. And the mathematics is quite simple. It says that t is of order m Planck uh, 4 times m Planck divided by g squared. And this is supposed to be less than 1, so this is larger than the Planck mass. So what does it mean? It means that if there were temperatures in the early universe which were of the order of the Planck mass or larger, then this rate, the gamma, the interaction rate, production rate of the gravitational waves would be so large that we indeed produce gravitational waves within a given Hubble time such that they can equilibrate. If some rate is as large as the Hubble rate, then those particles are in equilibrium. However, if we are below it, then the rate is much less than the Hubble rate. And now, in particular, there's a famous constraint on the scale of inflation. Well, in fact, inflation also produces gravitational waves, and so one of the constraints is from what we call R is a ratio of tensor perturbations over scalar perturbations. And tensor perturbations are just gravitational waves. And I suppose these are things that Yvonne will be talking about next week. But so there is this constraint, and the constraint is then that it converts into saying that the scale of inflation, let's say energy scale of inflation, is roughly speaking 10 to 15 GeV, roughly speaking 10 to minus 4 times the Planck mass. Maybe it's even stronger, but this is like a quite conservative scale. And so if there is inflation, like during inflation, we shouldn't really talk about temperature, maybe, usually at least, because the expansion is very fast. In any case, the temperature most likely is not much above the inflationary scale. After inflation, for sure, the universe reheats, but often it takes a while to reheat. So it's quite unlikely that the reheating temperature, the temperature that we reach after inflation, would be much above this scale of inflation. And so it's considered quite unlikely that the temperature Tmax. So usually we think then that the Tmax is somehow of this order of magnitude. And if that's the case, then we learn that then we are somewhere here, and then the gamma GW, it scales with 1 power less than the Hubble rate. And so if we are 4 orders of magnitude below the equality, then this means that this one also is 4 orders of magnitude below the Hubble rate. And so therefore, the gravitational waves do not equilibrate. But they are still produced. They are still produced, and the higher the maximal temperature, the more we are producing them, the closer they are to equilibrium. But if the temperature is in this domain, they are not equilibrated, but then the spectrum, the amplitude of the spectrum that I plotted in the beginning, it then depends on it scales with the Tmax. And so one day, if we were able to measure actually this background, then from its amplitude we could deduce what was the maximal temperature of the universe. Okay, good. So I think I will stop there. Of course, this was now a very different style from the previous lectures, but I mean, at least I wanted to show that these tools are actually, they are necessary in some cases to determine this kind of processes correctly, even to leading order. They are interesting because sometimes they allow you to do a simpler computation. In particular, if you just want to find out the log. And they have applications, and this was a peculiar application because at the end of the day we find a signal which is most likely not detectable in the foreseeable future, but very much the same techniques can also then be used are being used in many other computations, models for dark matter, leptogenesis, and so forth. So I hope that gives some flavor about these tools. So now, are there questions at this moment? Yes, yes. I mean, I didn't explain it yet. I didn't explain, and however, I expect that it will be explained next week in the lectures on the. But so inflation does many things, but in particular, Yvonne is talking about inhomogeneities, and inflation generates inhomogeneities. And then we know a lot about inhomogeneities from the CMB, and then so we know some, and the usual thing we see in the inhomogeneities is what we call the scalar perturbations. So just density perturbations, these are scalar perturbations. But then inflation also produces tensor perturbations, in other words, gravitational waves. And these gravitational waves, in a certain frequency domain, actually it's very, very small frequencies somewhere, like in my plot, it's really to the left. They have an indirect influence on the CMB photons, because the photons, they would propagate in this background of the tensor of the gravitational waves, and that turns out to influence the polarization of the CMB photons. And so from the measurement of the CMB, one gets an indirect constraint on how much there are gravitational waves around, and this is this ratio R. And now it turns out, like similarly, in analogy with my computation, I mean, we found in this computation we found that the amplitude of the gravitational waves, since it's suppressed by the Planck mass, then it also scales with the other scales of the system. In my computation, it scales with the temperature. But now in the inflation computation, there is no temperature normally, and then it scales, however, with the scale of the inflation. With the inflation has also, there's a vacuum energy density there is a scale of inflation. And so if the scale of inflation is higher, you produce more gravitational waves also from inflation, and that gives more tensor perturbations, and that would be indirectly visible in the CMB. And so then this ratio, this is strongly constrained with some number, 0.05, some number. And so that constraint then constrains the scale of inflation. And so this should be an upper bound. So it's an upper bound. Yes. And then that in turn, when we then think about how the inflation converts into a thermal medium, it also has an upper bound on the temperature. But these are, of course, model dependent statements, so they are not like easy to make rigorous. But let's say in many inflationary models, in most inflationary models, there's this kind of a constraint. From that, it follows this kind of a constraint. So quite, let's say, a great majority of cosmologists would say that the maximal temperature cannot be anywhere close to the Planck scale.
I was not 100% sure where the vertices between the gluons and gravitons really come from. So is it from contracting the energy momentum tensor with the metric when we compute the Lagrangian density, or?
Yes, I mean, you can do it in different ways, but the simplest thing is just that you write the, so one thing you can do is really to write, I mean, normally we write the, Lagrangian, but now instead we should write it in a covariant form. So then there is d4x, then there is whatever determinant of the metric, and then also here there is metric. So maybe it depends on where let's say I put fa mu fa rho sigma, then I would have to have metric here g rho u g sigma nu. And then, so I have metric here, metric, and then we write metric as, and then we write, first we write the metric as the, so in flat space we would write Minkowski. Now we cannot write Minkowski, we have to write here first the metric in, okay, Yvonne had here minus, so I had yesterday one, doesn't matter, AA, the usual, Friedman, Robertson, Walker, and then a perturbation. If we write the metric, then usually these are it's like 1, it's dimensionless number, and so the metric perturbation also, like we think about it as a relative change in the distance measurement, so then it would be dimensionless, but we have to rescale it to canonical dimensions, so that's where somehow this one of these h pi's divided Planck mass comes from, maybe like this. But anyway, so now you take this metric, and this is then your this is your graviton, this is my graviton. And so then I just take this and insert it here. But the problem is that it appears in so many places. It appears here, but it appears here, and of course the determinant is any power, infinitely many powers. But if you take the linear appearance, then it gets the linear appearance of H, then it couples precisely to the energy momentum tensor of this one. Yeah. And so that's where it comes from, yes.
Okay, so I want to ask about the detectability of this signal, because it's probably likely that we could have like another signal in this frequency, right?
Yes, I mean, but any other signal that, okay, so yes, so there are other signals which we know that are there, like astrophysical signals, for sure. Then there are a billion speculated signals which we don't know if they are there or not. Then this signal, it is there, gluons are there. There are gluons in this room, there were gluons in the early universe, so this signal is there. That's the nice thing about it. The problem is we don't know its amplitude, but it's there. So that's why it's nice to know about this. But now after doing the computation, indeed the amplitude most likely is so small that it will not be discovered in the next, I don't know, 20 years, let's say.
Okay, so at what time in the early universe exactly are we doing this calculation? Because I would guess this would happen before QCD is confined, because otherwise you don't have final state gluons, so you in particular can't really do anything with these diagrams, right?
Yes, exactly. So I'm imagining that I'm doing it. I want to do it as early as possible, because that's where I get the biggest signal, because really I have in these vertices the suppression by the Planck mass, and so the rate scales with the temperature, and I want to have a large rate, then I'm closer to the Hubble. And so I want to do it as high temperature as possible. So I hope that the temperature is 10 to 10 GeV, maybe 10 to 15 GeV, but certainly above GeV, certainly above the QCD transition.
And then in around that time, would you also expect like to have a large important background of gravitational waves just produced from inflation, which would then, because there's like graviton self interaction, so that could like really mess your signal up, or can we somehow circumvent that?
Well, the thing is that okay, I mean the background that you produce in inflation, like from vacuum fluctuations, it's famously flat. We call it flat. So in these some units, it's a flat spectrum here. Also, it's really important, like at very small frequencies. These are the modes which were outside of the horizon for a long. At some point, if you look at, I mean, if we look at very large frequencies, it's very long time ago that they were within the horizon, if ever or so. So this inflation background is important at small frequencies, and then sometimes, usually in most models, it then at some point it stops. But this thermal background, and not only the thermal background, very similarly also backgrounds, people do some reheating dynamics or preheating. I'm sure that Dani Figueroa will tell you a lot about preheating production of gravitational waves. These are then produced at much higher frequencies. So actually the peak here in terms of hertz is like 10 to 100 gigahertz. And so in this domain, you are not so much interfering with inflationary gravitons. They are very soft, but you are quite likely interfering with gravitons from some dynamics related to reheating, preheating, whatever dynamics ends the inflation. and the possibility that the system thermalizes immediately after inflation is kind of one of the ways of ending inflation. But maybe more realistically, there is more complicated dynamics ending inflation. And then that would also modify this shape. So it's not the only possibility for producing something in this domain, but typically whatever ends inflation, it tends to produce frequencies at high end of the spectrum, at the high end of the spectrum. In fact, yeah, right. And so this 10 to 11 is really like exactly the same frequency range where the CMB photons are, and so it's not a it's not really a coincidence, because if we produce anything which is at some moment in the history of the universe at a thermal scale, then as the universe expands, then the kind of the purely thermal shapes, they remain the same. Somehow the frequency redshifts just like the momenta redshift, and what we see today, just from the shape we cannot deduce at which time it was produced. You would get the same shape if you produced it at 10 to 15 GeV or 2 GeV. It's in the amplitude that tells us when it was produced.